So, again, going back to our illustration of a binary system, there they are on orbits that are the same shape but different sizes, both going around the center of mass. The line between them always passes through the center of mass instant by instant by instant. And furthermore, the position of the reduced mass in its orbit around the system mass, big M at the origin, is always the same as the position of mass 2 relative to mass 1. Now, which one you call mass 2 and mass 1 is up to you, but typically we make the smaller mass M2, and so if this is M1 and this is M2, then I don't know if there's some, yeah, they're all spacebar did it, okay. Then at this moment, the position vector of mu is this vector right here. From M1 to M2, that vector right there, move it over to the origin, that is the instantaneous position vector of mu. A little later, the position vector of mu is this vector, shifted over to the origin. So take all of them and shift them over to the origin, and that itself will trace out an ellipse which has a semi-major axis equal to the sum of the semi-major axes of the two orbits. You would just add them together. So at this moment, here is the position vector of mu. Take that vector, move it over to the origin. You just do that. At every point, you keep taking that relative position vector, move it to the origin. What do they trace out? They trace out the relative orbit, which is an ellipse that has that same eccentricity, same shape as either one of the two ellipses, but its size is the sum of the sizes of the two ellipses, or in other words, its semi-major axis is the sum of the semi-major axes of the two ellipses. Does that make sense? Yes?
So if you wanted to go back to a two-body, could you do that?
You can, yeah. We're gonna write down the equations that basically tell you, okay, if I know the parameters of the one-body problem, here's how you translate that into two-body quantities, and you can go backwards too. You can invert it. As long as you, you can invert it, because if you know the system mass and the reduced mass, that's two quantities, and there's two unknowns, M1 and M2. So you can always invert and solve for what a given value of mu and m uniquely specifies M1 and M2, and vice versa. So you can always go back and forth between the two descriptions. Yes. Meanwhile, it's so fun. Whee! I'm running out there. Damn, I ran out there. Not quite enough.
M2 and
Whee! The viewer can put in their own sound effects.
Yes, sound effects not included.
Sound effects not included, that's right. All right, let's zoom out. Let's zoom out here and go back to our story. Yeah. And now I will make it absolutely impossible to pay attention to what's on the board, because the video is going to have that happening the whole time. And it's kind of hypnotic. So I don't know if you guys will be able to pay attention to me either, but I'm just going to leave it there to keep making that impression. So I wonder if I can grab one of them.
You got it.
No, doesn't seem to work. All right, anyway.
Only there were pieces of junk.
Yeah. It's garbage.
Shit.
Okay. Now, so, as I was asserting there, and you kind of imagine from looking at that, the relative orbit, the orbit of mu around M. So in other words, there's there's M fixed in space, fixed in place by magic, space-time nails, space-time nails. There's mu. Mu orbits M on the relative orbit. Relative orbit of mu about M. Where was I? Yeah. Has A is equal to A1 plus A2, and E equals E1 equals E2. So the relative orbit is bigger than either orbit alone. In fact, its semi-major axis is the sum of the semi-major axes of the two orbits around the common center of mass.
Is that E?
It's E, yeah. E, the eccentricity of the relative orbit is the same as the eccentricities of the two individual orbits, which are the same anyway. So for these guys right here, the relative orbit would have a semi-major axis whose length was that plus that, the sum of the two semi-major axes. So it would have exactly the same shape, but it would be a bit bigger, because it would be the sum of the sizes, if you will, of the semi-major axes of the two orbits. And as we'll see, it's a great simplification to only have to keep track of mu. And again, you can always, if you know where mu is, you can figure out where M1 and M2 are. You can always go backwards and forwards each way. We've put the center of mass at the origin. Capital R equal to 0. We have, as we asserted before, M1R1 plus M2R2 is equal to 0. Again, the center of mass has the denominator being M1 plus M2, but if the whole ratio is equal to 0, then the numerator is equal to 0. So we only need the numerator. M1R1 plus M2R2 is equal to 0. But remember we said that R is R2 minus R1. So that says that we can write that R2 is equal to R1 plus R. So let's substitute that in above. So that says that M1R1 plus M2R1 plus M2R is equal to 0. Just plugging in R2 is R1 plus R in the expression that the center of mass is the origin. So now we can write that R1, because now we've just got R1 and R in our expression, so we can put R1 in terms of R. R1 is equal to minus M2 over M1 plus M2 times R. And so this is doing as promised. In other words, if I know the value of R figure out what the value of R1 is. I can go from the equivalent one-body problem to back to the original two-body problem. If I know where R is, I know where R1 is. So here I just solve this for R1. This is M1 plus M2, the quantity R1, plus M2R is equal to 0, so I just divide through by M1 plus M2 and write that R1 is minus M2 over M1 plus M2R. And we have that R2 is equal to R1 plus R. One way to get it, there's more than one way to get this. So if we write all that out, well, now we know that R1 is equal to minus M2 over M1 plus M2 times R. So we can write this as M1 plus M2 over M1 plus M2 minus M2 over M1 plus M2 times R. What am I doing here? Right, so in other words, here I've just put in that R1 is minus M2 over M1 plus M2, and here I've just rewritten R as M1 plus M2 over M1 plus M2 times R, so that I can have them over a common denominator. I'm just reading, in other words, that first one is obviously 1, but I put him over a common denominator. And so now I can add numerators, and I get M1 plus M2 minus M2, which is just M1. So in other words, R2 is equal to M1 over M1 plus M2 times R. And it makes sense that one of them has a minus sign and the other one has a plus sign, because remember, with the origin at the center of mass, the two position vectors have to be going in opposite directions. So one of them is going to need the minus sign and the other one's going to need the plus sign. But a better way to write this is to use our definition of mu. With mu being M1, M2 over M1 plus M2, that was our definition of mu, we thus have that we can write R1 is equal to minus mu over M1 times R, and R2 is equal to mu over M2 times R. And that's what I'm going to draw the box here. That's the probably more useful relations, which are entirely equivalent to what we have over here. So these are the two relations where if I know what R is, I can then figure out what R1 and R2 are. The equivalent one-body problem wouldn't be very useful if you couldn't translate it back into the original two-body problem. But wait, there's more. Let's rewrite the energy. Okay. Now we rewrite the energy. OMGZ! I am so excited. How to make class pseudo-exciting no matter how much, right? No, this is good stuff. It is actually good stuff. I like this stuff. So in terms of the one-body problem, energy will be the sum of the kinetic energies plus the mutual gravitational potential energy. So, what's the generic expression for kinetic energy? 1/2 m v squared. So there will be a 1/2 m1 v1 squared and a 1/2 m2 v2 squared. And so this is in the one-body problem, just from first principles. And then the gravitational potential energy is minus g times the product of the masses divided by the distance between the masses. And the distance between the masses is the magnitude of the vector r2 minus r1, because r2 minus r1 is the vector connecting the two bodies. So the distance between the bodies is the magnitude of that vector, r2 minus r1. Any questions? Now what would be nice is if the formula for the energy is also what you would just get if you had big M and big M and mu interacting. And since big M is fixed, all the kinetic energy belongs to mu. So you would want it to be 1/2 mu v squared minus g big M mu over r, the distance between them. Let's see if that works. And it does, because why would I be doing this if it didn't work out? But from above, we have, if we look at our expression for R1 over there, take a dot. We have R1 dot is equal to minus mu over M1 times R dot. Or in other words, that V1 is equal to minus mu over M1 times V, where V is that relative velocity of mass 2 relative to mass 1. And similarly, R2 dot is equal to mu over M2 times R dot. So that says that V2 is equal to mu over M2 times V. So notice that the R's and the V's essentially have the same relation to one another. In other words, R1 is minus mu over M1 R. V1 is minus mu over M1 V. And similarly for V2. The V's and the R's have the same relation. Put another way, the ratio of the velocities of the speeds is also the reciprocal of the ratio of the masses, just like the ratio of the distances from the center of mass is the reciprocal of the ratio of the masses. This is all if you put the origin in the center of mass. If you put it on Alpha Centauri, stop it. It's different. Don't do that. Bad. Don't put the origin on Alpha Centauri. Or Sirius. Yeah. Or Canopus. Or 3 inches to the right of the center of mass. None of those. They're all bad. So, okay, over here. We can say that E is 1/2 M1 V1 squared. Well, V1 squared, when I square it, when I just take magnitudes and square it, or dot it with itself or whatever, that'll just be this whole thing squared, so mu squared over M1 squared V squared. So 1/2 M1 times mu squared over M1 squared V squared. And similarly, 1/2 M2 V2 squared, well, V2 squared is just mu squared over M2 squared, V squared. V again being the relative velocity. for M1, M2 over R there in the gravitational potential energy, there's nothing stopping me from rewriting it as G times M1 plus M2 times M1, M2 over M1 plus M2, because then the M1 plus M2s just cancel each other, so I haven't like undone anything, times 1 over R, where by R I mean how far apart the two masses are, because that is the magnitude of R2 minus R1. And in fact, note that because of the way we've set up the equivalent one-body problem, the distance from M1 to M2 is the distance from mu to M. Because in the equivalent one-body problem, the distance from mu to M is the same as if you were riding along with mass 1 and seeing where mass 2 was at all times. So those are the same. The distance from mu to M is the same as the distance from M1 to M2. The relative displacement we set is the distance from M to mu in the equivalent one-body problem. Any questions? So let's rewrite up there. So this is, each term has a mu squared in it, so we've got 1/2 times mu squared times, this is m over m1 squared plus m over m2 squared. So that's 1 over m1 plus 1 over m2 v squared. Because in this first term we've got m over m1 squared, that's 1 over m1. In the second term we've got m2 over m2 squared, that's 1 over m2. Minus, and then, what do we call that? What's m1 over, m1, m2 over m1 plus m2? That's mu. And what is m1 plus m2? Big M, that's big M, that's the system mass. So notice that's G mu over R, which is exactly what you would get for the gravitational potential energy between masses big M and mu. So we get minus G mu over R. And the other thing to realize is that 1 over m1 plus 1 over m2 is in fact 1 divided by mu.